Hi everybody and welcome to this 8th video of BIOB20. In this video we're going to talk about ranks and their behavior. Let's start with an example that takes 5 random Gaussian numbers. The numbers are showed here. Since the numbers are random, the chances are that if I sort them they will change position. For instance, the third element gets in first position, the second element remains in second position, and so on. The way I can know the position that they will occupy in the sorted order is the function rank. Notice that the length of the function rank is the length of the input sample. The rank of the first element is 3. This means that that first element goes into the third position in sorted order. The second element remains in second position. The third element goes to first position, and so on. This is really what you would expect the rank function to do, intuitively. I will now define another Gaussian random sample, but this time the values are going to be much higher, by 30. If I look at the ranks of the vector y, I can see that I again get the numbers between 1 and 5, because this is the position of the elements in sorted order. But if I combine x and y together and then take the ranks, you can see that the first 5 values are 1, 2, 3, 4, 5, and the last 5 are 6, 7, 8, 9, 10. Not in that order, of course. This is because the elements of x are way below the elements of y. We do not know in which order the elements of x are going to come, but we know that they will occupy the first 5 positions. The same goes for the elements of y. We don't know their order, but we still know that they will occupy the last 5 positions. If we reproduce a similar example, we always get the same result, which is that the numbers 1, 2, 3, 4, 5 are in the first half, and the numbers 6, 7, 8, 9, 10 are in the second half, always. I can now reduce the gap between the two samples and see what happens to the ranks. When the gap is equal to 5, you can see that we still get the pattern that the first 5 numbers are in the first 5 positions, and the next 5 numbers are in the next 5 positions. But when I reduce the gap to 2, I can see that the pattern now breaks. There is a 9 in the first half and a 5 in the second half, for instance. On average, the numbers in the first half are still lower than the numbers in the right half, but the separation is no longer strict. If now I reduce the gap to 0, I get 2 identical samples in the left and in the right. And now the ranks are completely random. This is just a random permutation of the first 10 numbers. So to recap, when the 2 samples are exactly identical, the ranks of the first half are going to be the same on average as the rank of the second half. But when the 2 samples are separated by a gap, then I can expect that the ranks of the first half are going to be quite different from the ranks of the second half. What's interesting is that this does not depend at all on the distribution that I'm using. I can replace the Gaussian by the uniform distribution, and because the 2 samples are taken from exactly the same distribution, then the ranks are going to be the same on average in the left and in the right half. And again, if I introduce a large gap between the 2 samples, I'm going to have the same pattern as before, that the first 5 numbers are going to be in the first half, and the next 5 numbers are going to be in the right half. In summary, I can use this method to measure the gap between 2 samples. Just by looking at which ranks are on the left and on the right is going to give me an indication whether these samples are separated by a large gap or by no gap at all. And the main interest of this approach using the ranks is that this does not depend on the distribution of the samples. Next, we are going to speak about p-values, their distributions, and the power of a test. What is nice in R is that we have access to an array of tests, and the t-test is one of them, for instance. We can use the function t.test to calibrate the t-test when the null hypothesis is true. If both samples are taken from a Gaussian distribution with mean 0 and standard deviation 1, the null hypothesis is true, and we should accept it. We run the test as showed here, and when we press enter we can see a whole summary of the t-test. And to make a decision we just need to pick off the p-value from this output. If I just want the p-value, I can access it with $p.value. With this method, I can easily sample p-values of the t-test when the null hypothesis is true. If I want to obtain these p-values a large number of times, I just have to use the function replicate with n equals 100,000, for instance, and then plug in the whole t-test and the extraction of the p-value. To keep all those values, I assign the content to a vector that I call p.val. After a moment the command terminates, and I can show the histogram of the p-values. As you can see, this is a uniform distribution. We have exactly the same probability of getting any number between 0 and 1. So when the null hypothesis is true, we expect the p-value to be a uniform random number between 0 and 1. Let us see what happens to the distribution of the p-values when the null hypothesis is false. Here I'm shifting the sample on the right by 1 unit, which means that the null hypothesis no longer holds. In this case, the distribution of the p-values is far from uniform. There is an accumulation of p-values that are close to 0. We can still get p-values that are close to 1, but there is a relatively strong enrichment around 0. And this is a good thing. Remember that the null hypothesis is false. Ideally, we should reject it, and we reject the null hypothesis when the p-value is small. That is to say, close to 0. If I work with level 1%, I will reject the null hypothesis whenever the p-value is below 0.01. So I can count from the 100,000 p-values that I just generated how many of them are below 0.01, and that will give me the fraction of the time I reject the null hypothesis in this case. And this is 28.4% of the time. That's nice. The null hypothesis is false and I reject it more than 28% of the time. At least when the level is 1%. If the gap between the two samples increases, we expect to reject the null hypothesis more often. It's going to be easier to spot that the two samples are different. If the gap increases to 2, the rejection rate increases to 92.4%. And we can keep increasing the gap. If I go to a gap of 3, you could see that the rejection rate goes above 99.9%. I'm now going to test multiple values between these two extremes of 0 and 3. I create a vector mean, that is the sequence of numbers from 0 to 3, with an increment of 0.1. I create a vector that I call rejection rate, and that has the same length as the vector mean, and it contains only the value NA for not a number, because I haven't yet filled the number with proper answers. This is called the initialization phase. And I will now fill the vector rejection rate using a for loop. For I in 1 colon length mean, that is, I will take all the values from 1 to the number of different means I've got, then I will have in the body of the loop the command that I defined above, except that I will not compute mean equals 3, but mean equals mean in position I, so that is the ith value in the vector mean. And finally, I store the result of this complicated operation in the vector rejection rate at position I. This takes a few minutes to run, but here I fast forward it. I can then plot the rejection rate against the mean. I define x equals mean, y equals rejection rate, the vector has been filled now, and type equals L for lines. The line starts at exactly 1% when mean is equal to 0, and it rises to 1 when the mean gets close to 3. This graph shows the probability of rejecting the null hypothesis for different gaps between the two samples. This is called a power curve. The very first point on this curve for the mean 0 is fixed by the level that we have defined at 1%. For instance, I can plot a red line at height 1%, and you can see that this crosses the curve exactly when mean equals 0. This is just to show that the height of the first point is indeed 1%. This has to be the case when the null hypothesis is true, that is to say when the mean is 0, there's no difference between the two samples, we have to reject the null hypothesis with a probability of 1%. We can see what happens when we change the level of the test. We're no longer going to use 1%, but we're going to use 5% to see how the curve changes. I add a line to an existing plot, so I'm using the function lines, and I'm saying that I'm plotting the new rejection rate against the mean, which is the gap between the two samples. So I say x equals mean, y equals rejection rate, and col equals 4 for blue. The blue curve is completely above the black curve, meaning that we have a higher probability of rejecting the null hypothesis throughout when we increase the level from 1% to 5%. The first point of the curve goes through 0.05 at mean equals 0, and we can show this with the command abline at a position of 0.05, again in red. The main point here is that when we increase the level from 1% to 5%, we increase the probability of being wrong, in the sense that when the null hypothesis is true, we're more likely to reject it. But by doing so, we have also increased our probability of being right when the null hypothesis is not true. In this case, we have a higher probability of rejecting the null hypothesis throughout, so we are better off when the null hypothesis is false. This is the kind of information that we can get in such a power curve. We can choose a level that makes sense for the magnitude of the effects that we're looking for. That's what I wanted to share with you. Good luck with the quiz, and see you at the lecture.